Good morning, guys. So it looks like folks are just starting to come in. So I'll go ahead and get started with the basics of the day. Look, no, that's not what we wanted to do. Hold up. All right, that's fine. Here we go. Okay, so today we're going to look at some more complicated improper integrals. In particular, I'm going to show you how to mix type 1 and type 2 integrals. I'm going to show you how to handle type 1 integrals that are bilateral, meaning go to infinity on both sides. And how to handle type 2 integrals that have problem points in the middle rather than at one of the bounds of integration. And then we're also going to start developing some theorems on convergence of these improper integrals. And while both of these things are going to consume a meaningful amount of time, it's really the second item here that we need to be especially concerned with moving forwards, because the type of logic that we're going to apply in these convergence theorems is the type of logic that we're going to be using down the road when we talk about series. And infinite series really are the thing in this course that scare people the most. So think of the latter half of today's class as a primer or an introduction to the style of thinking we'll be using for the most part between now and the second exam. I want to move quickly because there's quite a lot to do. So first, how do we handle integrals like, or integrals of the form integral from negative infinity to positive infinity of f of x dx? There's more than one correct answer here. And to outline the contrast between the two, I want to show you some specific examples. So I'm not going to answer this question yet. In order to answer that question, I want you to think along with me about what should be true of the integral x dx taken from negative infinity to infinity. Remember, we always begin by writing these as limits. And if the area that the integral measures is finite, we like to say that the integral converges. If the area that the integral measures is infinite, we say that the integral diverges. That was the kind of basic thing that we talked about last time. We said it's always useful to draw the graph. So let's do that. Everybody should know what the graph f of x equals x looks like. Looks like this. And of course, if I want to integrate from negative infinity to infinity, well, that means I'm going to find all of this area and all of this area, right? This is the picture. So I'd like to take a poll. I'm not going to use an official poll here. We can do it quickly. But show me using a react, thumbs up here, if you feel like this integral should diverge. There's no wrong answer. I promise you, there's literally no wrong answer here. I'd just like to know what you guys think. There's two different ways of thinking about it. Brian makes a brilliant point here in chat. So I see Daniel and a handful of other people feel that this integral should diverge. Brian makes an interesting point here that if I were to integrate just from like here to here, say, and what I'm doing is definitely integrating an odd function about an interval that is symmetric about 0. If I was integrating just from -4 to 4, this would be 0, right? If I integrate from -10 to 10, this would be 0. If I integrate from -1,000,000 to 1,000,000, this would be 0. So show me with a thumbs up react if you think this integral should converge and have value 0. Davis, Matthew, Solomon, Georgia. Yeah, okay. So neither answer is correct. Neither answer is wrong. I'd like to be clear about that. One of the things you're going to discover as you move higher and higher and higher in mathematics is that 1 + 1 isn't always 2. There are spaces, algebraic spaces, where 1 + 1 is 0. Sometimes shit can get a little funky. And this is one of those places where shit can get a little funky. What I mean by that is there's more than one correct interpretation. I'm in the second camp. I would say that this integral is 0. But it depends on how you interpret it. Our textbook disagrees with me. And so those of you who said that this integral is divergent from the perspective of our textbook are correct. If you were to integrate symmetrically from -r to r, so here's two interpretations. Integral -∞ to infinity of x dx could on the one hand be thought of as the limit as r goes to infinity, integral -r to r of x dx. And then the integral from -r to r of x dx is 0 for every real number r. So this would be lim r to infinity of the constant function 0, which certainly is 0. This approach is called symmetric integration, symmetric bilateral integration. So an integral like this from -∞ to infinity is called a bilateral integral. And if you integrate those symmetrically, meaning you're thinking of this as being always from -r to r and then just expanding out, expanding at the same speed on both sides, then it is 0. On the other hand, you can think of the integral from -∞ to infinity of x dx as the integral from -∞ to 0 x dx plus the integral from 0 to infinity of x dx. And then each of those should get their own limit, lim r to -∞, integral r to 0 x dx, plus lim s to +∞, integral 0 to s x dx, both of which diverge. Neither one is wrong and neither one is right. It's just two different ways of thinking about the situation. Our book and all undergraduate calculus books take the second position as their definition. Or interpretation. So our textbook would say that this is a divergent integral. And the thing you want to remember here is if any one part of an improper integral diverges, then we say the whole integral diverges. Okay, and that's the approach that we're going to take in this class. That is the standard undergraduate approach, and it's perfectly reasonable. So is the symmetric interpretation, and the symmetric interpretation has some advantages, but it also comes with some complications. So rather than trying to push the symmetric perspective on you, we need to get comfortable with the standard interpretation first. So
what does it say under your arrow actually, where the integral is? It was the last part of the limit.
This is lim r to negative infinity, and this is lim s to positive infinity.
Okay, so the top portion's s and then 0.
Right. So the way we're going to handle bilateral integrals is to split them into the integral from negative infinity up to somewhere, plus the integral from that place up to positive infinity. And then the thing you need to keep in mind is that in this class, if any part of an improper integral diverges, then the whole integral diverges. In other words, I'm never going to say the infinite area above the x-axis cancels the infinite area below the x-axis. If any region of the area is infinite, then the integral diverges. And in a sense, that makes life easier on you guys, because you don't have to worry about different sizes of infinity canceling each other out. That's the sort of subtle thing you can get into trouble with in that first interpretation. All right, so this is how we think of it in this class. Now you go on to take a graduate class in real analysis or analytic number theory or anything like that, you may see other interpretations like the symmetric interpretation, which are equally valid. But you got to learn to walk before you can run. So the safe thing to think about is if any part of your integral diverges, the whole integral diverges. Or you can say if the area is infinite, I don't care whether it's positive, negative, cancels or anything. If the area is infinite, the integral diverges. All right. So for us, bilateral integrals from negative infinity to infinity of f of x dx will always be split up as the integral from negative infinity to a f of x dx plus integral a to infinity f of x dx. And then we always use a different variable for each of the infinities. So this would be like lim r to negative infinity, integral r to a f of x dx plus, plus limit s to positive infinity, integral a to s, f of x dx. And you can choose where to split. A doesn't need to be 0. Sometimes you want to split at 1 or at 5 or negative 2. But you split up an integral from negative infinity to infinity so that you only have one infinity in each integral. And then you can handle each of those according to the rules that we have from Wednesday. And then the thing to remember is if any part of the integral diverges, the whole integral diverges. Okay? So with this in mind, let me grab a problem from your textbook. There's a bunch of these that I like. No. Do they have any bilateral integrals in here? I think they do. Oh yeah, that's a fun one. guys are probably sensing my fondness for arctangent at this point. How would I do this problem? What's my first step going to look like?
Breaking it apart?
Good, yeah, we need to start by splitting this up. And I could split it up at 1, or at 2, or at negative pi. But the most convenient place to split this, I would say, is at 0. So I'll split it as the integral from negative infinity to 0 plus the integral from 0 to infinity. And then each of those pieces will get their own limit with their own variable. So limit r to negative infinity, integral r to 0, 1 over 1 plus x squared dx, plus limit s to positive infinity, integral 0 to s, 1 over 1 plus x squared dx. The antiderivative step isn't hard here. Antiderivative for 1 over 1 plus x squared is the inverse tangent of x. So this will be inverse tangent of x evaluated between r and 0 plus limit s to infinity inverse tangent of x from 0 to s. And you may over time get tempted to not write your limits. You may over time get tempted to be a little bit sloppy with the notation and leave off some of this stuff. But please don't do that. Right? If you get sloppy with this stuff and you don't write your limits, or you don't use separate variables, or you just try to move the infinity symbol around without the formal limit stuff, I will have to take off points. I don't want to do that. So please be careful, be patient, write everything out. The evaluation step here is not too hard. This is the inverse tangent of 0 minus the inverse tangent of r plus lim s to positive infinity inverse tangent of s minus the inverse tangent of 0. What is the inverse tangent of 0? We needed this on the test.
0.
Good, yeah, this is 0. And this is 0. What is the limit as r goes to negative infinity of the inverse tangent of r? Here's the graph of the inverse tangent function. What happens as we run off to negative infinity?
It heads towards negative pi over 2.
Good. And at the upper side, we're going to positive pi over 2. So this first piece is 0 minus negative pi over 2. And the second piece is positive pi over 2 minus 0. So altogether, I end up with pi over 2 plus pi over 2, that's pi. Okay. So what would I say about this integral? Does this bilateral type 1 integral converge or diverge? Yeah, he converges. And has value pi. I'm taking the limit of the inverse tangent function, Solomon. So as r goes to negative infinity, the inverse tangent of r, this piece, goes to negative pi over 2. That's why I drew this graph over here. So as we walk all the way off to the left on the graph of the inverse tangent function, my y values get closer and closer and closer to negative pi over 2. This piece goes to negative pi over 2 as r goes to negative infinity.
Can I have like 2 minutes to finish writing it down?
Sure. Okay, good, good. Yeah, I'll give just a second or two more here to write. Any other questions or comments on this problem? No, Brian. So what I'm saying here is that the limit as r goes to negative infinity of the inverse tangent of r is negative pi over 2. And the limit as r goes to positive infinity of the inverse tangent of, or sorry, limit as s, the inverse tangent of s is positive pi over 2. So that's kind of all this stuff here. Let me think about this. Highest and lowest points of tangent are. It sounds like you're kind of thinking about the unit circle there, maybe, Brian? I'm not sure what we mean by -1 and 1. The original tangent function has a range of negative infinity to infinity, right? Remember, the original tangent function has that like S-shaped graph. And so the inverse tangent function has this shape. And the inverse tangent function's behavior as you wander off to the left and off to the right is what's giving us the pi over 2s here. I know that trigonometry here at Santa Fe is not especially good, especially when it comes to inverse trig functions. It's very possible to finish the class here without really understanding those. So you might want to revisit those topics. Now I do have under the review material link in Canvas in our modules, a link to Paul's online math notes where he discusses the inverse tangent functions and their graphs. Highest and lowest points are at pi over 2. Sort of. So there isn't actually a point that has y value pi over 2, but this horizontal asymptote is pi over 2. So as you go all the way off to infinity in this direction, the y values do get closer and closer to pi over 2. Or if you think on the unit circle, the top and bottom points are associated with the angles positive pi over 2 and negative pi over 2. But that's several steps removed from thinking about why these limits are what they are. So in order to really understand these limits, you have to begin with the graph of the tangent function, restrict its domain, then invert it. In other words, we really need to get comfortable with this function in its own right, independent of the unit circle. So remember, regular tangent has a graph like this. This vertical asymptote's here, and then he's periodic. The vertical asymptote here. The VA here. So this is y equals tan x. This is negative pi over 2. This is positive pi over 2. So we restrict the domain to just this stuff. Then we find the inverse of that function. That is this guy. And that's where we're getting the limit. But you're correct that on the unit circle, the north pole is associated with the angle pi over 2 and the south pole is associated with the angle negative pi over 2. That is true. The unit circle interpretation of the regular tangent function is as the slope of the line from the origin to the terminal point. And so the slope of those vertical lines are infinity and negative infinity if you want, but it's a bit of a stretch to try and get there from there. We really do need to understand this graph on its own. Okay. So I do have to move on. The next thing I'd like to look at with you guys is the similar problem for type 2 integrals. So are there any other questions on this fellow? Okay. I don't want to discourage questions. Questions are always good. It's just that sometimes the answer is we need to go back and review something, and that's okay. There's nothing wrong with that. It's human nature to forget things, and especially if you were never taught them well, it's human nature to not know them. So don't feel bad about it. It's just that the trigonometry classes here aren't super solid. So I don't blame any of you for not having a lot of comfort with inverse trig functions, but we do need to develop that. So the analogous issue is, how do we handle integrals like, I'll say just integral a to b f of x dx, where f of x has an infinite discontinuity not at a or at b, but at some c where c is between a and b. So we saw how to handle type 2 integrals, integrals of functions with infinite discontinuities at the endpoint, right? If you have an infinite discontinuity at b or an infinite discontinuity at a, we saw how to take care of that last time. But what we haven't seen is how to handle something like this. So maybe I want to integrate from a to b, but at some value c in between those, my function blows up to infinity or negative infinity. So something like this. So rather than having the problem at one of our bounds, we have the problem somewhere in between. And based on how we handled the bilateral integral, you might be able to guess how we're going to handle this. The idea is, again, that we're going to split it up. We're going to split it up into two integrals, each having a problem at just one endpoint. So the answer is we split into the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And then handle each of those the way we were treating them on Wednesday. This would be a limit as r approaches c from the left of the integral a to r f of x dx plus the limit as s approaches c from the right, integral s to b, f of x dx. So the picture is kind of like this. So if your problem point is in the middle, you split the integral up, and then you get two type 2 integrals of the sort we dealt with on Wednesday. So instead of integrating all the way from a to b, I say, oh, well, I'd like to think of that as the integral from a to c plus the integral from c to b. And then in the integral from a to c, I handle that the way we were on Wednesday, meaning I integrate up to some variable just to the left of c, and then I let that variable sneak over. And in the integral from c to b, I integrate from some variable just to the right of c, and I let that sneak over. So r comes in from the left and s comes in from the right. An example like this would be the integral from -1 to 1 of 1 over x to the 2/3 power. Here, 1 over x to the 2/3 has a problem at 0, right? The bottom is 0 when x is 0. This thing blows up at 0. The graph of 1 over x to the 2/3 looks like this. Looks a lot like the picture we drew up there. And I want to go from -1 to 1. So I've got a problem on the left and a problem on the right. So I split this into the integral from -1 to 0, 1 over x to the 2/3 dx, plus integral from 0 to 1, 1 over x to the 2/3 dx. And then each of those will get their own limit using their own variable. This would be the limit as r goes to 0 from the left, integral -1 to 0, and then 1 over x to the 2/3, that's x to the -2/3, plus the limit as s goes to 0 from the right, integral s to 1, x to the -2/3 dx. And now each one of these I can apply the power rule to. This would be lim r to 0 from the left. -2/3 plus 1 is +1/3. So this is going to be x to the 1/3. And then I need to divide by 1/3. That's the same as multiplying by 3. So that's the antiderivative of x to the -2/3 is 3x to the 1/3. And I evaluate this from -1. Oh, I'm sorry, this guy should be an r. From -1 to r. So the upper bound here should be an r. That's the point of this limit. Plus limit as s goes to 0 from the right, the antiderivative here is the same. I add 1 to negative 2/3, I get positive 1/3, so I'll have x to the 1/3. And then I divide by 1/3. That's the same as multiplying by 3. And I evaluate this from s to 1. So when I do my evaluation step now, this is lim r goes to 0 from the left, 3 times r to the 1/3 power minus 3 times negative 1 to the 1/3 power plus limit as s goes to 0 from the right, 3 times 1 to the 1/3 power minus 3 times s to the 1/3 power. Okay, so as r goes to 0 from the left, what does r to the 1/3 go to? What is the limit of this piece? So this is again going to come down to knowing our graphs. The graph y equals x to the 1/3. That's the graph of the cube root function. He looks like this. So if I'm a little dude on this graph walking towards 0 from the left, what is my y value approaching?
0.
Yeah, it's 0. It's because this power is positive. No. If this power was negative, then yeah, the limit would be infinity, or maybe negative infinity. But because the 1/3 power here is positive, this is just 0 to the 1/3, which is 0. And then I'll have minus 3 times, what is negative 1 to the 1/3 power? What's the cube root of negative 1?
1.
Negative
Negative 1.
Negative 1, yeah. And then on the other side, as s goes to 0 from the right, s to the 1/3 also goes to 0. So this will be 3 times 1 to the 1/3, the cube root of 1 is 1, minus 3 times 0 to the 1/3, which is 0. So at the end of the day here, what we will have is 3 times 0 minus negative 3, which is plus 3, plus 3 minus 3 times 0. This piece is 0, this piece is 0. So you get 3 plus 3, or 6. So here, this integral converges. And its value is 6. So all those little limit details from chapter 2 of the textbook, back in those first few weeks of Calc 1, those are all very important here. And they're going to remain important for the rest of the class. So other things you might want to consider putting a little extra review time into, in addition to the inverse trig functions, would be those limit details. Make sure you know your graphs well enough that you can sort out limits. Remember, on the test, you won't have access to graphing utilities. So while it's okay to Google something while you're working the homework, here's my suggestion. Every time you have to look something up in the process of doing the homework, make a note. Right? I recommend having a little notebook, or I've got a stack of Post-it notes that I use for this sort of purpose. Every single time you have to Google something, write it down. Had to Google this, had to look up the graph of x to the 1/3, had to look up graph of 1 over x to the 2/3. Write those things down, then that's the shit you want to study for the test, because those are the gaps that need filling. So don't feel bad if you got to look some stuff up, but make note of it. Remember that you had to look it up, and then study that stuff before the test. A useful fact here is that the limit as x or r or whatever goes to 0 of x to the p is going to be 0 for any p which is positive. And that could sort out the limit here and the limit here, because the value of the power here is positive. Okay. So the last thing I want to do before we start developing our theorems, if there are not any other questions on this, is to explain how to handle when you mix all these things together, a bilateral integral with a problem point in the middle. Are there any other questions on this example? Okay, we're doing good. Everybody feels nice and comfy with this guy? So here the problem point for this integral was at 0, which was not either of those endpoints, but a number in between those endpoints. So we split it up at that problem point and then give each of those split up integrals their own limit. This last thing I'm going to look at how do we handle all this stuff together? In a single problem, in a single integral. And the best way to show this is through an example. So like the integral from -infinity to infinity of 1 over x plus 2 dx. First, it is a bilateral integral. It goes from -infinity to infinity. So that means I need to split up and use 2 different limits. Also, the function 1 over x plus 2 has an infinite discontinuity at x equals -2. So that requires splitting up and 2 limits. So you're going to need 4 limits here altogether. 4 separate integrals, each with their own limit. We split this as, let me draw the graph here. So -1, -2. And I want to integrate from -infinity up to -2 then from -2 all the way out to infinity. So there's kind of four problems. There's the problem at -infinity, the problem at 2 approached from the left. So problem at -infinity, problem at 2 approached from the left, the problem at 2 approached from the right, and the problem at positive infinity. So I'd begin by thinking of this as the integral from -infinity to -2, 1 over x plus 2 dx, plus the integral from -2 to infinity, 1 over x plus 2 dx. But now this guy has two problems, and this guy has two problems. So I'll split them further as integral -infinity to -3, 1 over x plus 2 dx, plus the integral from -3 to -2, 1 over x plus 2 dx, plus the integral from -2 to -1, 1 over x plus 2 dx, plus the integral from -1 to infinity, 1 over x plus 2 dx. Now each of those integrals only has one problem, and the problem is at the endpoint. So the -infinity problem is taken care of in this integral, and the integral doesn't have any other problems. The -2 from the left problem will be taken care of by this integral, and he doesn't have any other problems. The -2 from the right problem will be taken care of by this integral, and he doesn't have any other problems. And the positive infinity problem is taken care of by this integral, and he doesn't have any others. This looks tedious, and it is tedious. So before I could proceed, my next thing would be to give each one their own limit. So I would say this is the limit as q goes to -infinity, integral q to -3, 1 over x plus 2 dx, plus the limit as r goes to -2 from the left, integral -3 to r, 1 over x plus 2 dx, plus the limit as s goes to -2 from the right, integral s to, what would say, s to -1, 1 over x plus 2 dx, plus the limit as t goes to positive infinity, integral -1 to t, 1 over x plus 2 dx. And then I solve each of those integrals. And then I take each of those limits. And if any one of those diverges, remember the whole thing diverges. Which means if you were to go ahead and evaluate just this piece and find that he diverged, then you could stop. You wouldn't need to bother calculating any of the rest. All right, I'm not going to finish this problem. It's not an exciting problem to finish. The purpose here is just to show you how to set these up in the case where all the things are mixed together. So go ahead and make sure you've got this written down. Make sure you understand how and why we're splitting like we are. This is -3, this is -2, this is -1. So I chose to split at the two whole numbers that are near my infinite discontinuity and at -infinity and infinity. Are there any questions on this split? Why we needed any one of these four integrals or where any one of them came from? Okay. Then I'm going to move to something different. We're going to change gears. And before I get to writing things down, I want to look at some graphs. So I'm going to come over here to Desmos. And draw some pictures. Just say 1/x. I'm going to put this in black. I'm going to be thinking about type 1 integrals done from 1 to infinity. So maybe I'll add that. All right. What do you notice here? Let's just look at these two to start. Here's 1/x, and here's 1/x squared. One over x squared is smaller than 1/x, right? Everywhere, at every x value, to the right of 1/x squared is below 1/x. So whose integral would be larger? The integral of the black function, 1/x, or the integral of the blue function, 1/x squared? Which would have a larger integral?
1/x.
Yeah, the black function, right? The black function has more area underneath of it. The area under the blue function is contained within the area under the black function. And then the 1/x cubed, he's smaller still. So let me ask you a question. If the area under the blue function is finite, what can we say about the area under the green function?
That is finite as well.
Yes.
Good. All right. What about the purple function? If the area under the black function is infinite, what can we say about the area under the purple function?
That is infinite as well.
Correct.
Good. You're ready for a theorem. This says if 0 is less than or equal to g of x is less than or equal to f of x on the interval a to infinity, then if the integral of f of x from a to infinity dx converges, then the integral from a to infinity of the smaller function g of x also converges. That was the claim that we made about the 1/x squared and 1/x cubed integral, right? Because the one area fits inside the other area. If the big area is finite, then the smaller area must also be finite. And if the integral from a to infinity of g of x dx diverges, That implies that the integral from a to infinity of f of x also diverges. So if you're sure that your function is smaller than another function that has a convergent integral, the integral of your function must also be convergent. And if your function is larger than an integral or than another function whose integral you know is divergent, then your integral must also be divergent. Before I show you an application of this theorem, there's another theorem that I want to show you. So integrals of the form integral a to infinity 1 over x to the p dx are called p integrals. These converge if p is bigger than 1 and diverge if p is less than or equal to 1. The two theorems here are useful together because you can use the p integrals as a basis for comparison. Before I get into this, I'd like to prove the second theorem for you. It's not a hard proof. First, if p is equal to 1, then the integral from a to infinity 1 over x to the p dx is the integral from a to infinity 1 over x dx is equal to limit r to infinity integral a to r 1 over x dx. And the antiderivative here is the natural log. So this is the natural log of r minus the natural log of a. And we saw last time that as r goes to infinity, the natural log of r goes to infinity. So this is infinity minus the natural log of a, which is infinity. So these diverge if p is equal to 1. So p integrals diverge if p is equal to 1. If p is not equal to 1, then the integral from a to infinity 1 over x to the p dx is a power rule integral. That's limit r to infinity integral a to r 1 over x to the p dx, which is limit r to infinity x to the negative p plus 1 over negative p plus 1, evaluated from a to r. Because 1 over x to the p is x to the negative p. You use your power rule. You add 1 to that power and you divide by that new power. So this is lim r to infinity. I can pull out the 1 over negative p plus 1 as 1 over 1 minus p. And what's left is r to the negative p plus 1 minus a to the negative p plus 1. Now, a is just a number. It's not 0, right? So here I should say a is greater than 0. A is a positive number. So we're thinking of things like the integral from 1 to infinity, or 2 to infinity, or 5 to infinity. So this piece I don't need to worry about. But the limit, I'll have, I can pull my 1 over 1 minus p out. And then I have limit r to infinity, r to the negative p plus 1 minus something finite. I don't care about what a to the negative p plus 1 is. This limit depends on p. If p is greater than 1, then negative p plus 1 is negative. Let's see. So if p is bigger than 1, like 2, 3, 4, then you would have negative 2, negative 3, negative 4, plus 1. Those are all negative values. So r to the negative p plus 1 would go to 0 as r goes to infinity, because that power is negative, right? Like 1 over r squared, 1 over r cubed. If p is 2, then this is negative 1, and I would have 1 over r. 1 over r does go to 0 as r goes to infinity. If p was 3, then negative p plus 1 would be negative 2. So it's 1 over r squared, which again goes to 0 as r goes to infinity. If p is 4, then this would be 1 over r cubed, which again goes to 0 as r goes to infinity. So the integral would converge. If p is greater than 1. If p is less than 1, then negative p plus 1 is positive. So r to the negative p plus 1 is r to some positive power. You go to infinity as r goes to infinity. So the integral will diverge if p is less than 1. And then you put these three things together. If p is equal to 1, the integral diverges. If p is bigger than 1, then the integral will converge. And if p is smaller than 1, the integral will diverge. That proves the theorem. Now we're done. We've shown that if p is greater than 1, the integral converges. And if p is less than or equal to 1, then the integral diverges. So 1 over x is the magical tipping point. P equals 1 is the magical tipping point. If the power in 1 over x to the p is bigger than 1, then the integral will converge. If the power in 1 over x to the p is less than or equal to 1, then the integral will diverge. And you can kind of put that together with the graph pictures we were looking at. If you're above the above the 1 over x graph, you got to diverge because you're bigger than a divergent integral. And if you're meaningfully below the 1 over x graph, then the integral will converge. I think my dog is feeling a little bit rompy. Hey, Bubba. Okay, so now we're ready to play with an example or two. If this proof is frightening or confusing to you, you can breathe a sigh of relief. I'm not going to make you do anything with the proof, but you do need to know the theorem. You do need to know that these integrals, p integrals, converge if p is bigger than 1 and diverge if p is less than or equal to 1. And you also need to know and be able to use the comparison theorem. Both of these have a lot of intuitive appeal, but you need to be very careful. If an integral isn't exactly in this form, it's not a p integral. So if there's like a sine of x upstairs or a 5 upstairs, it's not a p integral. If there's an x minus 1 downstairs or anything other than 1 over x to a power, it's not a p integral. So let's do a couple quick examples. The integral from 2 to infinity of 5 over x squared dx. Now let me make that a 3 to infinity so we don't confuse ourselves with the 2's in multiple places.
I was almost finished writing down the end of the theorem,
Oh, sure.
like the second page of it. Sorry.
I'll zoom in a little bit. I'll show you, Brian. It will. We'll be able to make use of this. It's just that we need to be careful with the language. So yeah, you're not incorrect in saying we can pull out the 5. And once we pull out the 5, we will have a p integral.
Okay, I'm
The
good.
point is that we need to be very, very careful. All right. So here I can pull out the 5. This is 5 times the integral from 3 to infinity of 1 over x squared dx. This is not a p integral because it's not just 1 over x to some power. This is a p integral. So I can now say this is a constant multiple of a p integral with p equal to 2, which is bigger than 1. Thus, the integral from 3 to infinity of 1 over x squared dx converges. So our integral converges because 5 times something finite is something finite. But we really do need to be that careful. All the time, I see people mistakenly calling things which are not p integrals, p integrals. And while in this case it would not have hurt us, there are many cases where it will. So I need you to be this careful. Does that make sense? So while the integral we are given here is not a p integral, it is a constant multiple of a p integral. And so he will converge or diverge together with the p integral. Let's look at this guy, 3 to infinity sine squared x over x squared. This is also definitely not a p integral. But there's something kind of p integral-ish about it. the x squared downstairs makes me think of p integrals. I cannot pop the sine squared out because sine squared is not a constant. Does anybody have any ideas to what I could do? For this second example?
Could you make two separate integrals?
Well, remember, integrals don't split up over multiplication or division. I can't treat this as the integral of sine squared times the integral of 1 over x squared. That certainly doesn't work. But what are you thinking, Caleb?
Yeah, that's what I was thinking. Like, put sine squared of x times 1 over x squared, and then make two integrals that add up. Make that make sense?
Well, those things are being multiplied, not added. So I can't do that, right? I follow what you're saying. It is true that this is the integral from 3 to infinity of sine squared x times 1 over x squared dx. That's true. But this is not equal to the integral from 3 to infinity of sine squared plus or times or anything, the integral of 1 over x squared. That sort of stuff doesn't work. Integrals, right? Because these are being multiplied. Integrals don't split up over multiplication. That's why we have integration by parts. So this is no good. It's a common temptation though, so I'm glad you asked. And if these were being added instead of multiplied, then we could try something like that.
Use that first theorem that you showed us, right?
Yeah, so I keep trying to redirect to the comparison theorem here. The comparison theorem is the trick. We need to build an inequality. Sine squared of x is always smaller than 1 and always bigger than 0. Right? Regular sine of x is always between -1 and 1. Sine squared x is always between 0 and 1. This implies if you divide everywhere by x squared, that sine squared of x over x squared is smaller than 1 over x squared. Also, the integral from 3 to infinity of 1 over x squared dx is a convergent p integral. Here, p is equal to 2, which is bigger than 1. Thus, by the comparison theorem, the integral from 3 to infinity of sine squared x over x squared dx must also converge. Because this integral is smaller than this integral. Because this function is smaller than this function. Since my function is smaller than 1 over x squared, and the integral from 3 to infinity of 1 over x squared is convergent, the integral of sine squared x over x squared must also be convergent. The words that you write here matter at least as much as the calculation. You'll notice I didn't do any calculation in the solving of this problem. So this stuff we don't want to do. Let's be clear about that. That doesn't work. But without doing any calculation, I was able to say that this integral converges by comparing it to a p integral. And that's a really common trick. In fact, the last few homework problems in your set this week rely upon this trick. There are some subtleties here that we have not discussed, like why does it matter that there's a 0 on the left here? Why is there that 0 in the comparison theorem? I want you to think about that as you solve these problems. Let's see, so we're just about out of time here. Are there any questions you have for me on the solution of this problem?
So will there be like questions on a future test that only ask us to determine if a integral is convergent or not?
Absolutely. Yeah, in fact, as we move forwards through this middle part of the class, the question of convergence is way more important than the calculations. What that means is you need to become masterful with these theorems. You need to become very comfortable with the theorems, both the hypotheses, the stuff that comes after the word if, and the conclusions, the stuff that comes after the word then. And you need to be comfortable invoking them and writing the words that are necessary for the logic to flow. So this class is going to change from a calculation-based class to a logic-based class. And definitely the question of convergence is the primary one as we move forwards. Now, in some cases, you will be able to do the evaluation, but in many cases you won't. It's an unfortunate fact that you'll never find this integral exactly, not in terms of any finite expression. There's just no way to do it. It's been proven that there is no finite expression for that integral. Eventually down the road, I'll be able to show you how to do it as an infinite series, but it's quite complicated. So what matters for us at this point is that we start transitioning from thinking about calculation to thinking about theorems and logic. Write down these words as you solve these problems. It's the words that tie everything together and make it go. As you work the problems, don't hesitate to ask for help. Definitely share your solutions. Share them with me, share them with each other. I don't know if you have a GroupMe or Discord or anything like that, but please don't hesitate to do stuff like that. Talk to each other, share your solutions with each other. Try to challenge each other's solutions. Say, oh, I don't think that logic is completely correct, or this looks good, but what if that happened instead? Really push yourselves to make sure you're understanding this on a deep level. Write out all the words. Don't just let the words be implied. Write them out and make sure that the logic is sound. And again, if you're ever uncertain about something, or if you want to talk about something, come see me in office hours or send me an email with a picture of your work. I would really like to see that. I want you guys to be communicating these ideas, not just having them in your head, but make sure you practice communicating them, because that is every bit as important. All right, so we're entering the hard part of this class. We're going to buckle down and we're going to be okay. If you slack here though, it will burn you unimaginably hard. I've seen scores on the second exam in this class as low as 3%. Don't let that happen to you. You need to work hard. Don't let this burn you. Now is the time to start putting alarms in your phone every day to remind you when to study. Now is the time to make a friend in this class that you can email your work back and forth with, or chat with on Discord, or whatever it is that you want to do, to make sure you're sharing and effectively communicating your ideas and understanding them thoroughly. Okay?
Professor, one question before we leave.
Yes.
Can you explain to me how we concluded that this converges?
Sure.
This one right here, because I'm trying to figure it out, but maybe I'm missing something.
So I'm using this theorem, which says if my function is positive and smaller than some other function, and the integral of the bigger function converges, then it must be the case that the integral of my function converges.
Right, yeah. I get that.
Here, I'm able to show that my function, the function I'm trying to integrate, is smaller than 1 over x squared. I know that the integral of 1 over x squared converges because it's a p integral with p equal to 2, and 2 is bigger than 1.
Got it.
So
I
the
got it.
integral of the larger function converges. Therefore, the integral of the smaller function must converge. That's
Yes,
the logic.
Cool. Thank you so much.
Cool. All right. Any other questions before we sign out?
Oh, did you get my email? That's like on a personal note.
I did, Eddie. Yeah, I got it. Did you reply? So I sent you a reply and I'm waiting for a reply from you.
Yeah, I did.
Okay, I will send you a reply to your reply in these next few minutes and we'll get it sorted out, okay?
All right, thank you. I really appreciate it.
Of course. All right, guys, I got to get running. I hope everybody has a happy and safe weekend. Work hard on this stuff. If you get stuck on anything, don't hesitate to ask for help, okay? Take care, guys.